Well, hello everyone, and welcome back to Adrian's Digital Basement. If you're a regular watcher of my channel, you know that I had an Apple IIc when I was a kid. I was very fond of this computer, and to this day, I still have a special place in my heart for this little Apple computer. This particular specimen comes from local viewer James out of Eugene, Oregon, who recently gave me quite a large amount of things. James was actually moving and needed to clear out some space, asked me if I'd come down, and well, he very graciously donated a whole bunch of stuff. So this is the first computer we're going to be taking a look at, and well, it's got something wrong with it. And you know what I like to do? I like to figure out what's wrong with them and get them working. So without further ado, let's get right to it. So I have to admit, I've never actually seen this particular Apple IIc box. The one I had when I was a kid was the earlier box, which had red printing on it and had a picture of someone holding the actual computer. This picture of the Apple IIc just shows off how awesome looking this computer is. I really feel that it's one of the coolest looking 1980s computer. This is the Snow White design language, and it was very similar to the Platinum design language used on Macintoshes, but it originated on the Apple IIc, and this machine has a very light, creamy white color, or it did at least when it was new, and the monitor and the stand and everything just matched perfectly. Another nicety of the IIc was that Apple included a whole bunch of peripherals right inside the computer, and the optional mouse kind of shows that. On an Apple IIe, if you wanted to use this mouse, you needed an interface card, but on the IIc, it just simply plugs into the joystick port and just works. There are also two serial ports and a built-in floppy drive controller, so you have an internal floppy drive and you have an external connector to hook up to other floppy drives. But even better than that is the connector on the back of the machine is smart port compatible, so this thing supports hard drives right out of the box. And if you use something modern like a floppy emu, you could just boot this thing with 32 megabyte ProDOS hard drive images. Something on the IIe is much more difficult to do. You need a Lyran card, which are extremely rare and expensive. All of that is built into the IIc, and that's what makes it so cool. I just want to take a quick look at the rest of the box here. So we got Apple logos on the right and left side, and then on the back, we have a side profile view of this machine. And if you're unfamiliar with the Apple IIc, this is one of the things that's kind of interesting about it. It has a built-in carry handle, which doubles as a tilt stand. So you can operate the computer just flat on the desk, but if you flip the handle down, it actually will tilt the computer to be more ergonomic. I mean, for 80s ergonomics, it was better than average, at least. I find it interesting that Apple connected the power supply cable to this IIc, but no monitor cable. Why have a cable at all if you're not going to have it accurate? Because obviously, if you have a monitor, you need to have the video cable connected to this. This finger touching the computer thing was kind of something that Apple did, at least on the Apple IIcs. I'm not sure if this extended to all the other Apple II line, or the Macintosh for that matter. But yeah, just really remember seeing ads in magazines, I guess for the IIc always, and you always had that single finger reaching out and touching the computer. We have some copy here, which is kind of hilarious. The wizardry of Apple technology scaled in a new convenient size. With a built-in disk drive and 128 kilobytes of memory, real power for business, education, home, and entertainment. The Apple IIc personal computer runs thousands of programs from the Apple II library, the largest software library in the world. Well, that's fighting words. Does anyone think that this was actually true in 1985? I suppose this is possible because compared to, say, something like the Commodore 64, this Apple II could run software that was written for the very first Apple II machine back in 1977. The Commodore 64, on the other hand, could run some basic VIC-20 programs and maybe PET programs, but certainly not any programs that were written with assembly language for those computers could be run just easily on the 64. Just plug in and go. Set up in minutes, learn it in hours, and use it for years. Now it's simpler than ever to add video displays, printers, second disk drives, modem, mouse, joystick, and almost any other accessory you'd ever want. Just plug them in, no complicated installation, no need for add-on expansion cards, and the symbols on the back tell you exactly what goes where. Other than like the largest library in the world, the rest of this is pretty much true. If you were scared to open up your Apple II to plug an expansion card in, well, the Apple IIc was for you. Inside the box, non-eco-friendly packaging, but this was 1985, and you know, we didn't know better, I guess. Okay, grabbing the 2C out of the box, it's in pretty good shape, actually. The yellowing is minimal, but if we flip this over and look at the bottom side, this is a more accurate representation of the original color. And I had one of these in 1984, and I remember what it looked like, and definitely this has a little bit of yellowing. Unfortunately, Apple IIcs are quite prone to yellowing, just the way the plastic is or whatnot, so this is not too bad. As far as the box goes, there are no other accessories in here, no manuals, nothing else for us to look at. These are all the built-in ports that I mentioned, the mouse port / joystick port, the modem, there's a video output, it's not RGB, but allows you to hook up an RGB to HDMI, composite video, floppy drive, printer, power, and a power switch. And then internally we have an ALPS mechanism, 5¼ single-sided floppy drive. It's just nice that all that stuff's built in, so when you get one of these, you don't have to worry about having to procure various cards. So for instance, if you want to use a program like ADT Pro to copy stuff onto this, you can just make a cable that hooks up to a PC, and then you can transfer disk images directly over the serial port without having to buy an Apple Super serial card, for instance. Now, some of these machines have ALPS keyboards, which I think this one does, and some do not. I think one way you can kind of tell, and I don't know if this is a foolproof method, is that on the bottom of the earlier Apple IIcs, the label is actually kind of a metal label with some printing on it. And the later machines that appear to have ALPS keyboards have the label itself embossed into the plastic, and then you just have a serial number sticker. I know there are at least 2 revisions of the Apple IIc, of the original Apple IIcs. There was a later 2C Plus that has a built-in 3.5-inch floppy drive and an accelerator, but these original ones with a 5¼ floppy drive, there were 2 motherboard revisions. The later version of the motherboard, I think, has reduced number of RAM chips, but it also has an expansion header to have a third-party add-on RAM board, or maybe Apple made the RAM board, I can't remember, but Applied Engineering did as well. That would plug in, and then you could expand the memory beyond the built-in 128K. We have a note on this machine. It says bad characters. This was put on by James, I presume, not me. And I noticed that the case is kind of not assembled correctly. So I guess someone has been in this machine before, maybe looking to see what kind of faults it has. The machine definitely is a little dirty and gunky. Something there as well, but nothing too serious. And these ALPS keyboards, they're pretty reliable and robust, although the switches can definitely get dirty, and then you have key switches that don't work properly. Let's pop one of these keycaps off, and we'll just verify exactly what kind of, yep, ALPS keyboard. It's the salmon switches. Luckily, I have a whole bunch of spare of these switches from some parts keyboards, so if I do need to swap stuff around, it's relatively easy to desolder these switches and swap them over. Same switches that were used on like the Macintosh SE keyboard, and I think the Dell Bigfoot, I think they were maybe black switches, and these are salmon. There's a bunch of different variants. And they feel really nice to type on. So like I said, if you're going to get an Apple IIc to do some basic programming on or whatever, this is the one to get. Okay, well, I mentioned I don't have a power supply for this, but I think if you've watched my channel before, you know that that is not that big of a deal, because the Apple IIc original power supply, I think, provided something like 17 volts DC, but this power supply that's in here is a DC to DC converter. And it doesn't really matter. You don't need to give it actually the 17 volts because, well, I made this little pigtail adapter. So this DIN is what goes into the back of the computer. And then I just have a 2.1mm barrel type jack that plugs in, and we just pop this in like that. And what I like to use, but you could do whatever you want, is just use a 12-volt power supply. Any kind of wall wart will work. This particular jack is center positive, but I have a little USB-C power delivery to the barrel jack, 12 volts, and frankly, that's all you need to power up a 2C. So we'll just plug it into the little power bank here. This will boot it up, and we can see there it's providing 12 volts. Now the computer is off, but let's turn it on. It just takes a second to negotiate there. We'll see how many watts it uses. Sounds normal. Looks like we're using 19 watts with the machine running. Oh, that was with the disk drive running. Without it running, under 10. So yeah, making one of these pigtails is really easy, and then I'm sure you have a 12-volt power supply kicking around. Obviously, a 2-amp or a 3-amp or whatever will be plenty for running this machine. And if you're worried about load, let's say 2 floppy drives, it's not a problem, because really only one spindle motor is running at any given time. Whichever is selected is actually spinning, so you don't actually run both floppy drives simultaneously. So I think having them both connected doesn't really have an effect on the power draw coming through the power connector. So we're going to use the RetroTink for testing this machine. So I'll plug in the composite video and let's see what we see when it comes to bad characters. setting up the input, if I pick composite, the text will be kind of fuzzy and it will support the color graphics that the Apple II generates, but I'll just pick S video here. That means we will only have monochrome graphics, but we will have a much sharper text. All right, let's see if this works. Certainly sounds okay. Oh, there are bad characters. All right, well, we have a few @ symbols and then we have some quotation marks with one that is flickering quite a bit. What I'm going to do is I'm going to write down what we're seeing character-wise because we should be able to decode what exactly is going on. Because the boot ROM clears memory and then prints Apple IIc at the top, check disk drive at the bottom because we don't have a disk in there. But we're getting @ symbols in some locations and then we're also getting quotation marks in others. It looks like we have 2 quotation marks and one of them is flickering. But what's interesting is, oh, look at that. So scrolling also has issues. This right away is telling us that most likely this machine has bad RAM. And the fact that there are 2 different characters that we're seeing, not just @ symbols, but also the quotation mark, tells us there's going to be at least 2 RAM chips that are bad, possibly more. The way the Apple II works, and this is the same for all of the Apple IIs, is that the text mode is just stored in main memory. Unlike some other contemporary 8-bit machines back in the 80s, this one does not have dedicated video memory. None of the Apple IIs do. The video subsystem uses the fact that the 6502 has 2 clock phases to actually access the memory essentially at 2 megahertz. These machines are 6502 based, they run at 1 megahertz, but the CPU is only accessing the RAM when the clock signal goes low or high, I can't remember which one it is, and the video subsystem accesses it on the other phase of the clock. But that essentially runs the RAM at double the speed and means that there are no wait states or slowdowns for the video subsystem when it comes to accessing the memory. This is different than, say, on the Commodore 64, where it does slow down a little bit. Sometimes the VIC-2 needs more time than is available, like during that off phase of the clock cycle. Most of the time I think it is okay, but sometimes it needs more time and it will actually halt the CPU while it finishes up what it's doing. And I think that's called Badline. So to get really accurate timing and the maximum performance on a 64, you actually have to disable the video, and you can do that and you end up just getting a screen that's just the border color. So it's not like the video goes away, but that gives the CPU full access to the memory without any slowdown. So for timing critical stuff, you got to do that because you just don't know when the video subsystem is going to tell the CPU to wait. On the Apple II, that is never a problem because the video subsystem is super simple. It's built into ASICs on this machine, but on the older ones, it's just TTL logic. And essentially, it's just running all the time. No matter what the CPU is doing, the video subsystem is accessing main memory and displaying it to screen. So if we take the CPU out of this computer, you'll actually still just see what's in main memory, which is going to be garbage when you first power up the machine. And that's one of the nice things about the Apple II. There's a lot of simplicity there. Now back to this problem we're seeing here with this bad memory. Interesting is the computer is actually working. The first 255 bytes of memory is called the 0 page, and that part of memory is really critical for operation of these machines. The ROM on this machine, and pretty much on all the machines, is going to heavily use that first 256 bytes of memory. So if you have any bad bits of memory in that first 256 bytes, then you're almost certainly going to get a crashing computer. The second 256 bytes of memory is also critical because that is the CPU stack. So when things push and pop stuff off the stack, it's going to be stored in that second 256 bytes. That means if there's a problem there, then almost certainly the computer is going to crash as well. So this is telling us that these bad bits of memory we have are in the higher parts of memory and most likely not in the 0 page or the stack, although they might still be. It's just the computer hasn't accessed those memory locations and therefore it hasn't crashed. Now, one thing about the Apple IIc is there are multiple versions of the ROM, and the later versions actually have built-in diagnostics. Let's see if we can actually run that. So to do that, you hold down both Apple keys and you hit Control Reset. And yeah, okay, we're getting the diagnostics. Oh, and look, it told us which bits are bad. Now your 2C and also like the 2Es might have a ROM that doesn't actually have the built-in diagnostics. You kind of get these repeating patterns on screen with this graphics mode, and I think it might say kernel okay, but it never actually tests the RAM. I don't know what it's actually doing, but either way, it's not particularly useful. But this one, on the other hand, you hold down both Apple keys, Control Reset, and if we had color mode enabled, we'd get multicolors, and very quickly this is telling us that we have 2 bad bits. Now, somewhere out there on the internet, there's probably information about which bit is the least significant bit and which is the most significant bit. So is the 0 on the far right side bit 0 and bit 7 is the one on the far left, or the other way around? Let's make an assumption that this is the least significant bit in the error message we saw, and that is the most significant bit. So it shows us that the bad bits that we're dealing with are D6 and D5. And by D, I mean data line. So these are the RAM chips that are connected to those data lines on the CPU. Now, when we open this computer, there's going to be some RAM chips, and we're not going to know which one is connected to which data line. But looking at the pin out of the CPU and the pin out of the RAM chips, it will be very easy for us to just tone out with the multimeter to figure out which is D6 and D5. And we can actually use the fact that we have these bad characters with the @ symbol and also the quotation mark. Now, remember, I guessed that there were 2 bad RAM chips, and the diagnostic is also confirming that. But let's try to figure out using the ASCII values of space, @ and the quotation mark to see which 2 chips are bad based on this information, what we actually see. And the good thing about this is, for instance, if we had a ROM that didn't have the diagnostic, we'd still be able to figure out which are the 2 bad RAM chips just from these alone. And one thing I want to add is there might be more bad bits than just the 2 bits that result in those 2 characters instead of spaces, and those might be outside of the video memory. That means that we wouldn't be able to necessarily see those, at least in text mode, on whichever page is loaded. The Apple II has 2 text pages and 2 graphics pages. So the one that it boots up into, I think, whatever is text page 0 or 1, or it's the first text page. And that location in memory is affected by at least 2 bad bits, resulting in space turning into these characters. But like I said, there might be others. So one thing I want to try, I want to drop into basic, is we are just going to type HGR. It's going to go to graphics mode. Well, we can see those bad bits visually represented, and they're flickering. And what happens is 60 times a second, the video subsystem reads out the contents of the entire memory buffer, the high-res buffer there, and displays it. So that means if the gates inside the RAM chip itself try to read out those cells and put them on the data bus, well, if it's fluttering, then you get, well, what you see there. But because we have just sporadic bits of memory that are bad, at least in the video page we're looking at here, and it also affects the text mode page, well, that causes the graphical artifacts in graphics mode and on text mode, but doesn't seem to have an effect on the 0 page in the stack, at least not in a way that makes the computer crash. So at least that means we have a working system, which is kind of cool. We also have at our disposal the machine language monitor, which is built into all the Apple IIs. Also very, very handy. This allows you to set and read back memory. You can also disassemble what's in RAM, which is what we're doing right here, which can prove useful in some circumstances if you have access to this. So you can read and write from memory with it, and then that can actually tell you which bits are wrong as well. But we don't even need to do that because our bad bits are visible right on screen. So based on what we see on screen, we can actually figure out which are the bad bits. Not to mention we have the diagnostic available as well. Now, when it comes to figuring out which are the bad bits, you might be tempted to think, oh, well, we had a space that turned into an @ symbol and a space that turned into a quotation mark. Let's just look at the ASCII table and figure out which are the bad characters. Well, here's where this is a trap for young players, as Dave Jones would say. The Apple II does not use ASCII when it comes to the character ROM. So when characters are stored in memory and then read out using the character generator on the Apple II, it is not ASCII, it's an Apple II thing. If you use the ASCII table to convert these to bits, so we can figure out which are the bad bits, you're going to get the wrong bits. So if you look at ASCII space and you go, oh, look, 001, 000, that means bit 5 is a 1 and bit 6 is a 0. And we know the diagnostics told us that bit 6 and 5 are the problem ones. You might be, oh, that's kind of cool. I think we're onto something. But not necessarily. It might actually work out in this case, but I'm not positive about that. So we know that the @ symbol is one of the characters that is showing up instead of a space, 01, 0000. So again, that's still telling us that's bit 5 and 6. And then if we look for the quotation mark, which is the other character we're seeing, well, that's where things kind of go off the rail a little bit, right? It's 0010, 0010. Well, here's the problem. When we look at the @ symbol, there are 2 bits that are wrong, right? Because the ROM sets up the space character in all of the cells except for the banner at the top. And we have a 0 instead of a 1, and then we have a 1 instead of a 0. So there are 2 bits that are wrong. But then for the quotation mark, there's another bit over here that's wrong. So that kind of shows that we have a 3rd bit that's actually problematic, because this one is correct, and the only thing that's changing is that one. So going off ASCII, it looks like bit number 1 is wrong, bit number 5 is wrong, and bit number 6 is wrong. We have 3 bad chips. I don't think that's necessarily the case. A quick search of the Apple II character set brings us to this Wikipedia article, and this is actually helpful. So what this is showing is the actual character set for the Apple II and the II Plus. It was generated by a Signetics 2513. And this gives you a little bit of an insight into the fact that the character map on the Apple II is very unlike regular ASCII, because it actually repeats 4 times, at least on the original Apple II. And it has an inverted version, it has a flashing version, and then it has 2 versions of just the same thing over and over again. Later versions added lowercase letters on the second set from the bottom here, But what you see here is a direct representation of what would be in memory. So if you store 00 in memory, which is a null in ASCII, it doesn't show anything, that should show you an inverted @ symbol on the Apple II at least. Now a little further down is the character set for the 2C and also the enhanced 2E. So we'll just worry about this particular one. I think where it shows up as black here is still inverted. So of course in text mode on the Apple II, you would see that as a white background, not as a black background. It's a little confusing there. Either way, I think the character set that this machine is currently running is going to be this one here that starts at hex 8x. So to use this, we got to write down the hex value of all these characters. So the @ symbol is hex 80. The space is hex A0. And then the quotation mark is hex A2. And we could use the Windows calculator or any of programming calculator to figure out the binary values of these various things. But here's where we run into a little bit of a problem. Well, we know this binary sequence stored in memory is what we should have for spaces, but we're getting an @ symbol sometimes. And that means that this bit is turned off, and this is D5. But then for the quotation mark, the bad bit specifically is D1, not D5, D1. I hope that makes sense because this middle one is the space. That's what everything should be. So if a bit is set wrong, like this is set to 1, then you end up with the quotation mark. And if that bit changes to a 0, then we end up with the @ symbol. So this is telling us that these are the two bits that are wrong, not D5 and D6. One possibility is I'm doing the conversion wrong and I'm reading this chart incorrectly, and that's quite possible. The other thing is, though, is that the diagnostic ROM, while it's running, is relying on the 0 page and the stack to do its job. And if that part of the memory has some faulty bits in it, just some subtle faulty bits, then what can happen is that can affect the way that it calculates and displays what is actually at fault. Because the ROM itself contains diagnostic code, it's not like it's going to crash for sure, but the problem is the calculations might rely on part of the memory that's faulty and is giving us incorrect readings. So just to rule out that it's not this character map that I'm using incorrectly, I'm going to do the same conversion again, but I'm going to use 2000 and 22. And here's the calculation if we're using that top set of characters, so 00, 20, and 22. It still tells us that D5 and D1 are the bad bits. The only thing that changes is the most significant bit, D7, is set to 1 if you want to have 80 and A0 versus 00, 20, and 22. So again, this doesn't quite match what's going on here. I am still not ruling out, though, that I am doing something wrong when it comes to reading this character map. So I think we should go to the machine language monitor and actually just try to store a character right into memory so we can look at what values are actually stored in memory for those characters in one of the text cells that's working properly. So then we can try to figure out and do the same math process here to figure out which bits are wrong. So we know the text screen, the top row is all working properly. There's no issues there at all. So I'm just going to run a little program here that's going to print a whole bunch of @ symbols. Oh, take a look. We actually have a problem on the top upper right character where the @ symbol turns into a B. That actually kind of implies that there might actually be a third RAM chip that's bad. So I happen to know that text page 0 is at 400 hex. So if we just type 400, that actually tells us what's stored in that upper top corner. So we type 401, I think that's the character that's 1 to the right of the top left corner of the screen. And if we look at 402, it should be a C0 as well. Yes, it is. Let's do that same thing again, but I will just have a blank space in the top corner. So we do 400 now, and we get A0. So A0 matches the space character that I had. If we push enter, in the top corner there is now with a quotation mark. So if we do 400 now, and we get an A2. Okay. So that tells us on the character map that we were looking at, definitely for the space and the quotation mark is A0 and A2. But how come when I filled the screen with @ symbols, we ended up with a C0 in the top corner as opposed to an 80? I think I just assumed that if A0 was space, that 80 was the @ symbol, but it looks like it's actually going down to the C0. So that means my calculation for which bits were bad was wrong, because instead of the 80, it is a C0. So we can erase that one since we know that is not relevant. And a C0 is 11000000. So this one is space. I know it's all getting a little confusing on here. That is space. That is quotation mark. And this down there is the @ symbol. So that tells us because the space should be a 0 there, and now it's a 1, that D6 is bad. And then we know that D5 is also bad because the bit should be a 1 for the space, and now it's a 0. But here's the thing. We have an extra bad bit because this quotation mark, which is an A2, is actually putting an extra bit there that should be a 0. So that's telling us that D6, 5, and 1 are all bad, and yet the diagnostics are not saying that. It is saying that we don't have a problem with D1. So I think this kind of confirms the diagnostic ROM is D7 to D0. So it's right on those, but what's going on with that one? I'm going to try to print a program here to just fill up the entire screen with quotation marks. I don't remember how to print a quotation mark to screen. It's probably like CHR $ and something specific. Okay, the U key, by the way, is very problematic. Yeah, it keeps typing multiple letters. Okay, so I'm going to put a quotation mark. Oh, that doesn't work. Come on. So theoretically, what this should do is I put like an F. Oh, okay, wait, I did something wrong here. Input. What did I do wrong? I forgot how to use AppleSoft Basic. I wonder if Basic's having an issue here specifically because of the RAM problem. That is entirely possible, to be honest. Okay, I just did a little lookup of that. Okay, there we go. We can print a quotation mark with that CHR 34. So let's try to fill the screen with quotation marks. So A0 is in the top corner because, yeah, it's a space. And everything after that is A2, like I had thought. So the only thing I was wrong on was the @ symbol. I thought it was 80, and it's actually C0. Here, okay, here's a test we can do. I'm just going to write FF to the character cell in the top left corner. Okay, and it prints the little hash symbol. Now, if we look at what we stored there, we get back an FF. So it is able to store all ones. Now I just stored a 00 there, which you can see is an inverted @ symbol. And if we take a look at that cell, we get back a 00. I think what's happening here is that cell's not bad. That cell's fine. It's just that when we fill the screen with, say, @ symbols, and then it scrolls, the Apple is copying the contents of the RAM for the lower lines, just moves it up a line. That means that if one of the cells below it in the text buffer is bad, then what happens is it will actually copy into that upper line. And we can test that again by just first writing like C0 into that memory space. That's the @ symbol. And then if I write A0 into there, it should be a space, and it is. And if I write A2 into there, it should be a quotation mark, and it is. Okay, that cell is working perfectly. Problem cell exists in that first column, and you can see it right there, where instead of it saying asterisk 400-55, there's a 2 there. So we can use that information because we know that should be an asterisk, and we're actually getting a 2. So let's go to our little conversion chart and check those bits. So according to chart, asterisk is AA, and it turns into a 2, which is B2. Well, the plot thickens a little bit because if the asterisk looks like it turned into a 2, that's an AA into a B2. Well, that's telling us from this little chart, what is this, D4 is bad? And then this one is turning into a 0, so D3 is bad. Well, that's even worse than before because we had D1, D6, and D5, and now we have D4 and D3. Wait a second. We can't have all these bad bits, right? We just can't. Okay, everyone, I see the problem. It was a 0, not an asterisk that changed. I bet people were screaming at the screen telling me that. So we have a 0 that turned into a 2, which is a B0 that turned into a B2. And that means instead of this, it's 10110000. So that tells us very specifically the bit that's in question is that one, which is D1, which coincides with what we had before. D1, D6, and D5. Well, again, it's not what the diagnostics are telling us because it doesn't tell us that bit's bad, but we're seeing evidence that it absolutely is bad. All right, so what I did is I moved onto this character space that has one of the bad characters. See, that's an @ symbol. If we put a space there, it becomes an @ symbol. If I put an @ symbol there, it's still an @ symbol. If I type a 1 there, it becomes a Q. If I type a 3 there, it becomes an S. So I'm just over this spot because I want to type some characters here and see what's changing how. So I'm typing a semicolon and it becomes a square bracket. And that specifically, I did a little calculation, I won't show it. It basically is telling us that, again, it's D6 and D5. Those two are both being represented incorrectly. So I'm relatively confident at this point that we do have 3 bad bits on this machine. This must be a bad RAM test that just misses the fact that this is bad, or it's getting corrupted by the fact that the memory has errors in it. Now, there's still another test I want to do. Let's exit out of this and go back to basic. I want to go to the 80 column mode because this uses the auxiliary memory on the machine. There's actually 2 banks of 64K, and the second bank is used for the alternating columns and 80 columns mode. So the 40 column text mode is interleaved with another set of memory from the auxiliary RAM, and then it becomes the 80 column screen. So those bad bits, if they're happening in the 40 column buffer, which we know they are going to affect 80 column mode but not every column. Now, the funny thing is when I hit Control and reset, it's going to drop back into 40 column mode. And we should look at all the characters that are bad on screen right now and see if they stay in the same place. Because what will happen is we're going to lose every other column. That's the 80 column mode disappearing. And we should be left with the same exact pattern. Quote, at, quote, at. And there it is, quote, at, quote, at. So that's telling us that the auxiliary RAM, the other 64K on this machine, seems to be working properly right now. Or at least the auxiliary memory's text mode buffer, this is what we're looking at there when we were in 80 column mode, it's okay. There could be bad bits in it as well, but certainly it's the lower bank of memory where we have the problem. If I put letters here, and I'm putting them on every other column, these are written into the auxiliary RAM, the second half of memory on the Apple II. When I hit Control reset, all those S's will disappear because we're looking at the 40 column buffer only at this point. And that is by design. That's the way Apple designed it. Okay, with this gives us an idea of which 3 RAM chips are bad at the minimum. There may be more, but it's at least these 3. Now the problem is when we open this up, remember there are 2 banks of memory. So there's 128K. Well, we don't know which of those 2 sets of memory is the primary memory, the first 64K, or the secondary, the bank switched memory. And I don't remember if the 2C has schematics available to tell us which bank of memory is which. So we might have to get creative to try to figure out which is the auxiliary and which is the primary memory or the main memory on this machine. All right, I'm going to open this thing up now. With all the screws out, opening the Apple IIc can be kind of annoying sometimes. There are some clips on the front edge you have to open, and it looks like someone's already done that. There's some screwdriver marks in here. So clearly someone's already been in this machine. So the way I just pop that clip is I just used a plastic spudger tool. And basically, I think if you push the top lip towards the keyboard, that can kind of help release it if you don't have a plastic spudger. So basically, you just jiggle the case around. The back is also clipped together, so it's kind of annoying. Just get the handle off there, and then there we go. Now the computer is, the top cover is off. Well, that's interesting. So that was never screwed in. I can't believe this machine was working. This is the power supply module, and it does have 2 screws that hold it in. Those had been removed. Okay, well, there's our 2C, and here is our Alps keyboard. And you can tell it's the Alps keyboard because look, it's got a nice PCB there. Everything is screwed in. It says Alps right there, and it has a nice, strong backplate. Well, lifting up the keyboard, we can kind of see our problem. We got empty RAM, everyone. Empty freaking RAM. So you just pull the connector off, keyboard comes free. I can tell that this is the earlier motherboard, does not have the RAM expansion slot on it. If I recall correctly, the later Apple IIcs use 2 4464 chips. That means 2 chips is 64K, so there's only a total of 4 RAM chips. On this one, the RAM chips go under the disk drive because, of course, there are 8 and another 8, so 16 total. Now, one thing I notice is it says MRD0. I wonder if this is main RAM data bit 0 and main RAM data bit 6, and there's data bit 7. So that's printed around the board. So we don't have to even guess or tone out which chip is connected to the CPU, which is right here, NCR65C02A. So of course what we have to do now is get the floppy drive out because I have to take the motherboard out and the motherboard is under the floppy drive. Now looking at our memory, we know it's all empty RAM. We know that we have 3 bad bits down here. Who knows about this auxiliary memory? We're gonna have to run a test program once this computer is able to boot. Right now, I didn't even try booting a floppy disk because there's no point. We have corruption in memory. Therefore, of course, it's not gonna run software. Now, luckily, we don't have to guess on which memory is bad and which is good because it's labeled very clearly, auxiliary RAM, main RAM, and they've nicely printed the data bits for us as well. Now, here's one problem you can run into with Apple IIcs. The memory and the floppy drive are very close to each other. So much so if you have to socket any of this RAM, well, you can't, because if you do, the floppy drive will not go back on. So if you change out any of the RAM in the auxiliary bank or even bit 7, because it's kind of under the floppy drive, you have to install these chips directly on the board. But we know based on this diagnostic work I did before, we have a bad chip there, a bad chip here, and a bad chip here. Now, before I go removing the motherboard and swapping out this memory, I want to try something. I want to run the Apple II dead test ROM on this machine with that bad RAM installed so we can see exactly what that diagnostic ROM tells us about what memory chips are bad on this machine. And to do that on the Apple IIc, it's pretty easy because we can use an EEPROM in place of the main ROM, the system ROM. Here's our system ROM, copyright Microsoft 1977, part number 342033A. I did a quick Google search, 342033A is ROM version 00. If you can believe it, ROM 00 is actually not the first ROM, it's the second ROM. The first one is FF, and that one I think is the one that doesn't have the built-in diagnostics. The 2C also has ROM 3 and ROM 4. I think ROM 4 is the version that works on the version of this machine that has the RAM expansion. I don't think it necessarily will work on this one, but definitely ROM 3 will, and I think ROM 3 brings additional functionality. Now, it's a 32K EEPROM, which tells us it's a 27C256, which absolutely will work on this board. And when it comes to the dead test ROM I was talking about, or the RAM test that I want to run on this, it's this ROM. And it's on my GitHub repo, but it's actually created entirely by my friend David Giller. And what this test does is it runs an extremely comprehensive RAM test on the Apple II systems. Now, it only tests the first 48K, but it doesn't require any working memory to actually work. Obviously, if you don't have working memory, you're not going to be able to display anything on screen. And what you see here is an animated GIF of the actual RAM test process. Now, it's doing a March U RAM test, which is one of the most comprehensive RAM tests that will be able to fix or identify all of the bad RAM that is on this machine, at least in the first 48K. Now, a couple caveats is it doesn't test that top 16K because that's banked, and it also doesn't test the entire other 64K, the auxiliary RAM on the 2C or the 2E. But when your first 48K is working properly, it's very trivial to boot a disk, and then you can load some third-party diagnostics that are on disk, and then that can test all the additional memory. When your first 48K has bad RAM in it, like it does on this machine, it's very unlikely that you're actually going to be able to boot anything. So to download the release, you just go to releases. It's version 1.01. There's a disk image, so if the system does boot, you can boot that, or there's a 2K ROM file available. Now, I've never actually tested this on an Apple IIc, but it should work just fine. So here's the dead test ROM, and the problem you're going to notice is it's only 2K. If you try to load this into a 32K EEPROM, it's just not going to work. Well, it will, but you have to load it into the EEPROM in the correct position. Now, looking at the hex editor, this is a 2K dead test ROM, and if we go all the way to the very end, you can see here these bytes. So there's a bunch of FFs, that's just blank space. But then we see 00F8, 00F8, and 00F8. What these are vectors for the 6502 processor. So when the 6502 is first initialized and comes out of reset, what it does is it looks at the very top of the memory space. And remember, 64K is the entire memory space of 6502. It looks at the very top and it's looking for a reset vector. And what the reset vector is a location for the program counter to load and then jump to start executing code. These are those three vectors, and one is reset, one is interrupt, and I forgot the other one, to be honest, but whichever, it doesn't really matter. I think it's the middle one that's actually used when the system is first powered on. What this is going to tell the computer to do is to set the program counter to F800 and then begin execution. Well, that happens to be the very top of this ROM file, or nearabouts. And for this ROM to work properly, and of course, that interrupt or reset vector to work properly, this needs to be situated at the very top of the address space in the 6502. Now, when you take a look at the ROM for the 2C, this is it right here. It looks like there's a bunch of developer names, actually. Kind of interesting. I don't think I ever noticed that. Well, it's a 32K file. We know the entire file can't be sitting in memory all the time because that would take up half of the RAM in the 6502. From my recollection on the Apple II, you have something like 12K of ROM space up at the top of the memory space. The part below that is for the expansion cards and the I/O and stuff like that. So there must be some bank switching going on with this ROM, or maybe it contains some ROM code for like the serial ports or the floppy drive controller or something like that. I don't know. The Apple IIc has a memory management unit IC on the motherboard, and that obviously is going to be handling things like mapping all of this ROM stuff into the appropriate spots. But what we can do is take a look at the very end of this file, and it looks like a lot of blank space there, and we can see if it has vectors, and it does. It's got the same three vectors. Now, these are pointing to C788, C78E, and C788. But one thing we know is that when the 6502 is first powered up and initialized on the 2C, this ROM is mapped into the top of address space. So at least this part of the ROM here is available at the very top. Or at least we know that this part of the ROM here is available at the very top of the address space, because that's what these vectors are doing here. They are there for the CPU to look at, and it's going to look at FFFC and FFFD. That's where these are going to be mapped to in the actual memory space to begin execution. So what I'm going to do is I'm going to select all when it comes to the dead test ROM, so all 2K, and I'm going to select the top 800 bytes of this file of the Apple IIc ROM, and I'm just going to delete them. So they're gone. And now I'm just going to hit paste, And that is now the dead test ROM at the top of the original Apple II ROM. So there it is. It starts at 7800 and it goes all the way to the top, 7FFF. So it's the same 32K size. It just now has the dead test ROM at the top. Now, another thing I could have done is just had a blank file as 32K and just pasted this into the top 2K. That probably work as well. Or I could just copy this 2K file 16 times and put that into a new file so it just be replicated over and over again. And that might work as well. Well, I think this might actually do the trick. And since I had the 32K ROM from the Apple IIc, might as well just use it. Out with the original ROM chip and in with my freshly programmed 27C256. Oh, one thing incidentally, check this out. See how this wobbles? What can happen is this press fit connection can become weak over time, and the ground connection is actually lost between this part, which is actually grounded to the motherboard, and the RCA jack. So if you're having issues with the video cutting in and out, it's usually this that's the problem. And what I recommend doing is just grab some solder and melt that onto the connector. You should be able to make a new connection between the RCA jack itself and the shield. And that should keep that nice and firm, and you shouldn't have the video cutting out anymore. All right, let's boot this thing up. We don't need to have the keyboard connected or the floppy drive. Let's see if this works. Ah. Well, that clearly didn't work. Did I flash the wrong file? Huh. So we are still booting the normal system here. So I guess the top of the ROM space, well, in the file at least, was not actually mapped into the top of the ROM space. I'm also noticing, incidentally, that it's only now detecting that one of the bits is bad. That's pretty hilarious. Let's power cycle this. Okay, so we still have the quotation marks and the @ symbol, so that's clearly wrong. Wasn't it detecting that 2 bits were bad, both 5 and 6? Okay, well, what we're gonna do is I have the file open still, and we're gonna look for another reset vector. There's gotta be another one floating around in this file. So I'd imagine it's gonna be on the 2K boundaries. And for instance, 7FF is the top of 2K. Well, those aren't vectors, so it's not that. And here's the next boundary, and it's definitely not that. And there we go. That's gotta be the vector right there. FA62, that's probably like the power on reset code. So I'm just gonna load the original ROM, and I'm gonna do that replacement process again. So there it is, from 3FFF down to 800 right there. So we have selected exactly 800 bytes, which is exactly the length of the dead test ROM. Can I just paste over this? Oh yeah, that worked. Okay, so the red stuff indicates that that's what's changed. So that's the dead test ROM inserted into the Apple IIc ROM. And at the very end, we still have those vectors there, whatever that is. I don't even know what that is. We will just leave that there. Instantly, if you're curious what happens on an Apple IIc if you turn it on without the ROM installed, you just get that. And you see that little bit of flickering that's going on there? That's the bad RAM showing up in graphics mode. And that's just the default mode on the Apple II when it's not initialized. Sometimes you'll get stuff like that. The state of the registers that control the graphics mode and text mode and stuff like that are kind of randomized. So you get just sort of random junk like that when you power it on. Same thing would happen if the CPU were not working, or really if it's not executing any code. This is what it looks like when the system is not initializing. All right, so the freshly flashed EEPROM is in with the dead test in the correct location. There we go. So it's running through the test, and it's in graphics mode right now, but you see spurious characters, spurious bits all over the place, and this should report exactly what it finds and tell us which bits are bad. Okay, our results popped up for a second. I took a screen grab. It's just gonna loop, and the one thing I'm noticing, I don't think the sound works, because the dead test ROM does beep when it boots up. So I think either the speaker is bad or this connector is bad. Okay, here's the RAM test results. Now, the problem is, of course, we have bad RAM. So some of these characters are going to be incorrect. Like we have these spurious @ and there's an M there, and there's probably going to be 2s and things where there shouldn't be things. But that's okay. We really just need to figure out, if we look at any of these banks, which bits are bad. Now, the funny thing is, we're back on the GitHub repo here, is that the speaker is relevant and useful for this ROM. If the zero pager stack are bad on this machine, it's going to use beep codes to tell you about the error. And see, if error is detected in the stack or zero page, you'll get a page error and it'll beep out the bit that is bad. And there it is. 1 beep is D0, 8 beeps is D7. Now, the locations it's mentioning here, by the way, are relevant for like the Apple II and the II Plus, not so much for the IIc here. So when it comes to the results chart, the way you convert these values into bit information about which bits are bad, it explains that down here. All you do is take the value, so like 8 is displayed there, and you convert that into binary. And that's going to tell you exactly which bit is bad. So bit 4, aka D3, is going to be bad. Now, so we have lots of errors, and they're all 20 or 22. There's a couple 02s up here too. Yeah, it doesn't really matter. The reality is, on a machine like this, all 48K is contained in that first bank of memory. But on an Apple II or a II Plus or a clone, it has 16K RAM chips, so you actually have multiple banks. So it matters where these are located to help you identify where on the motherboard the bad chips are. But on the IIc or IIe, it doesn't really matter because any bit that's wrong in any of these banks is going to be in that first 64K of RAM. So to convert which bits are bad, we type in like 20 hex, and that's going to tell us that data line 5 is the problem, or 22. That's going to be data line 1, data line 5 again. And actually, that's interesting because what I don't see on here, I think we had a 02, but that's just obviously going to be data line 1. I thought with my calculations here, we figured out without a doubt that D1 and D5 and D6 were bad. Well, that's interesting. That's very interesting. So remember, when I loaded BB into memory, we got back DB, and that was the square bracket. That's what we saw on screen. And without a doubt, to change BB to DB, you have to change both D6 and D5. So there are a couple choices here. We could either follow the diagnostic routines built into the machine and only change out the chip that it says are bad. I think that's not the right thing to do. Or we can follow the dead test ROM and do what it says is bad. Or we can do what I thought was bad and change out all 3 of the chips. I'm inclined to trust this dead test ROM first. So what I'm going to do is I'm going to swap out the 2 chips it says are bad, and then we'll just rerun this and see if it is magically fixed or we still have a fault. Maybe I should let this run another pass, because what's totally possible with the dead test ROM here is we just let this run, and I think what it does is it actually accumulates the errors. So if you have bits that are sort of sometimes bad or other times not, every time it runs, that table that shows up should have those extra bits accumulated. So I'll let this run for several passes and we'll see if any of those extra errors accumulate. While that's just running passes, I'm just going to quickly test the speaker here. 8 ohms, how about no ohms? That's just open. And even on the speaker contacts itself, it is open. So this is a faulty speaker, and that's annoying because I have a bunch of speakers, but I'm not sure I have any that are this size. Or do I? Actually, I think I do. That's probably the same size speaker. This came out of an old PC or something. Now, incidentally, getting these speakers out on the IIc is really quite difficult and annoying. You have to really pry it out. Oh, there we go. It came out not too bad. Yeah, let's just double check after prying it out. Yep, it's still 0 ohms. And let's check this little PC speaker that I have here. There we go. This one's 9 ohms. I know it's a little glary on the multimeter screen, but you could see that. Let me just double check this one more time. It's definitely open. No ohms. All right, the test is still running, by the way, and I went ahead and just attached these little wires onto this new speaker. So let's plug this in. Oh, okay. We do have a working speaker. And I don't know how many passes it's run, but I assume it's multiple, because it took me a little while to find the speaker and change the wire over. And the screen looked exactly the same. So we turn this machine off and on with the speaker hooked up. So beeps. That's what it should do. Incidentally, getting the speaker back in is even harder than getting it out. Super annoying, this little setup they have here. Okay, well, I'm struggling to get the speaker back in. I think it's easier when the motherboard is out. So I'm just going to remove the motherboard and try to get that speaker back in. It's extremely difficult. If anyone knows a trick, please comment down below. I've never figured it out, and I've watched people get it reinstalled, because I've taken them out before as well for retro writing, and I just had to force it back in and the speaker gets bent up. So if anyone knows the trick, please comment down below. All right, so I got it under that clip, and all that's left is this one, the easy one to get it under. Easy is a relative term. Oh, there it is, it's in. So I guess that's the trick. You have to really force it under these two and then try to get it around that one. I just want to make sure that it still works. Yeah, it's okay. All right, so dead test is telling us that these two chips are bad, and it's not even mentioning MD6. So I guess I'll start with these two, 1 and 5, and I will put sockets because it's fine. The disk drive's over here really, 7 onwards. You can't have sockets, you have to put those around the boards, but all of these can go on the board. So we'll start with 1 and 6, and then we'll see what the dead test ROM says. Okay, there we go. I've removed those chips, installed 2 sockets, and I put 2 new chips in there. These are the 2 bad chips. All right, let's see what happens with the dead test ROM now. Well, there's no spurious characters on the screen. Does that mean this thing's working? It doesn't have any flashing pixels or anything. Unbelievable. I'm looking at my notes. I obviously did something wrong with my little text mode visualization, figure out what bits are bad, calculations, and I should have just trusted the dead test ROM from the very start. And I can tell you pretty much guaranteed that the RAM test that this is doing on the first 48K is way better than any other RAM test that exists for this machine. It's possible there's like something new in the last couple of years that's maybe as good as this, but certainly when it comes to ROM-based testing like this, nothing compares to this particular ROM. I mean, I might be biased a little bit, but honestly, this is just great. It's so quick and easy. You don't have to have a bootable system. I could take this RAM out and it would actually be able to tell us which bits were bad. It's that good. Well, there we go. It's saying everything is fine now. So you know what that means? I'm going to take off the little Sharpie mark I have on this RAM chip here that I accused of being bad, which is clearly not bad. I'm just putting this machine back together. While I was trying to type some of those basic programs, not only is the U key bad, but one of these keys doesn't work at all. So typical Alps keyboard fashion, well, this thing is pretty dirty. We have keys that don't work, so that would be a separate repair, which I'm not going to get to in this video. What is cool about this Alps keyboard though is it has this really strong backplate and it actually clips into the floppy drive. So you don't get a lot of deck flex on this, probably one of the reasons why it feels so nice. There are other keyboards that are just like a PCB with some plastic stiffeners. Total junk. Okay, ROM has been swapped over. There we go. A little noisy on the spindle there. Check disk drive. Well, let's run the built-in diagnostics. I mean, it's obviously going to work. I don't think there's anything wrong. It's so funny that the built-in diagnostics were totally worthless. I am positive on the most recent time I was running this, it was saying that bit 6, D6 was bad. And the reality is I switched out D5 and D1 and the system is now working. So can't trust this test at all. Just can't. There it is, system okay. And if you want to run this again, you can just push both Apple keys and it will run again. Okay, whenever I have an Apple II on the channel, got to try Fat City. Let's see if that boots on this machine. That's normal. This disk always does that. I think it's going to work. Nice. Let's switch to color mode here. There we go, color. Colors are a little bit off. All right, let's try a different disk here. Okay, yep, locksmith, cool. What I need to do is find my Apple IIc diagnostic disk. Oh, I know what I can try instead. I have this, my SmartPort SD. This is a hard drive emulator that just uses a ATmega, very simple thing, open source project, and I just have a cable from an old floppy drive here. I don't know if this ROM 0 that's on here can actually boot off of a SmartPort disk like this. Let's give it a try. So it should fail to this and go to that. Oh, it is, it's working, the light's on. Oh, look at that, it's booting. Clock not found, all right. So I was hoping there were some utilities on here to maybe do some diagnostics. Here's a copy of Apple IIe Diagnostics. Let's try this because maybe this will actually work for testing the extended memory. Oh boy, that looks hard to read. What we need is the RAM tests. Apple IIc memory expansion card. Oh, this said Apple IIe Diagnostics, but it actually says Apple IIc at the top. We're going to do main logic board RAM test. So that put a 1 there because I think that's the test that is going to run. I don't think we really need any of the other tests. And I'm going to do B for selected tests. And here we go. It's going to test the RAM. I have no idea if this is actually a good RAM test, but we know we have a bunch of empty RAM in this motherboard, and let's see if it's good according to this potentially bad RAM test that Apple made. This is an Apple utility. Oh, we're in double high-res mode there, and I don't notice any flickering pixels or anything, so that's a great sign, actually. Test finished, which I assume means it passed. Let's test everything here in the video test. I just want to see that actually work. We'll change this back to composite mode so we can actually get some color out of this thing. Color bar test. Oh, well, that looks absolutely horrid. That can't be right. Character generator test is working, so that's mouse text at the bottom there with those graphical symbols. Don't worry about that flickering that we had there. Check 40 columns, press the 4080 switch. Oh, okay. So 40 column, 80 column. Low res graphics test. Well, this one's working, so I don't know why the color bars weren't working before. It's like a bug in this program. So those are the two pages. High resolution graphics test. That looks fine. Double high res. Well, that doesn't really look fine at all. I don't know. Okay, I don't think this testing works super well. What I'm going to do is switch the SmartPort SD over to disk 1. So you have power cycle it to do that. And that is total replay. So we'll have tons of games on there to try out. Saying it has 128K. Excellent. Colors definitely look off a little bit, especially the orange. It's kind of brown. So here's Rad Warrior, and what you're seeing there on screen is double high res, and that graphics looks fine. So that test thing we were running somehow broken. Rampage also is running in double high res, but wow, the colors look weird. Rampage itself should be in yellow, not that kind of limey green color. I wonder if there's a potentiometer on this thing to adjust the color carrier. If there is one, it's going to be near the back here somewhere. Oh, right there, hue adjustment. Okay, one direction was making it kind of greeny. Well, does that look a bit better? At least the Rampage is, oh, way better now. The orange is actually orange. And here's that title screen for Rad Warrior. So yeah, this looks so much better. It's weird how I adjusted the hue control and it actually made everything more vibrant as well and looks much better than it did. Okay, RoboCop, let's give this a try. I'm not sure which of these games actually is a 128K game that uses double high res. I think Rampage is one, but maybe RoboCop is as well. The title screen we just saw there was in double high res, which requires an enhanced 2E or a 2C with 128K of RAM. There it is, and it is definitely double high res. Double high res games are always pretty slow on the Apple IIc 2E. There's just a lot of pixels being pushed around by a 1 megahertz processor. I don't know how to move around, but the game is running. There's no way this game would work if this computer had any further bad RAM on it. So I'm going to say that all of this RAM is fine. Look how the timer is counting down so quickly. That's pretty hilarious. Okay, there's how you move. Look at that animation speed, everyone. Look at that animation speed. I have no idea what key actually punches. Oh, okay, it's Apple key. Maybe that's, oh, look at the jump. It's so slow. Yeah, double high res games, they are not great. So one thing about the Apple II is it's unable to sense more than one key at a time on the keyboard, but the Apple keys, because I remember I told you they were the joystick buttons, that does work. So I can push left or right and I can punch simultaneously. The spacebar also jumps. Isn't there a way to like change weapon or something? Because isn't the whole thing about RoboCop is he actually doesn't just punch things? Oh, look at that. Did I do that? Not sure how to shoot up or diagonally. Oh, I can shoot diagonally with the O key. Okay, item. Anyhow, okay, well, this 2C is obviously working properly. I'm just gonna finish putting it back together. So for getting these back together, start at the back, kind of lever it on, get it down in the bottom, make sure you have it all aligned properly. It can be kind of tricky, which is why the case was sort of bulged on one side when we took this thing out of the box. Well, there we go, it's back on. Oops, I forgot to put the handle on. I'm not gonna really put this thing back together fully because obviously this computer needs a good clean, but at least the case is all together there on that side. And then you just sort of push it down and clip it on the front like that and put the screws back in. Make sure you have, of course, a handle in there first. And that's it, the 2C is taken apart and put back together. Obviously, we do not have any bad characters anymore because this machine is fixed. And there we have it, a repaired Apple IIc. Turned out only 2 bad MT RAM chips, and luckily I didn't have to desolder anything that wasn't actually bad. I'm still a little surprised that my manual calculations on which bits were bad gave us false information. I'm editing the video and I realized what happened with my calculations, why I thought there was an extra bit that was bad. Well, it turns out when I first did the calculation, I got it correct. It was D5 and D1, which were the bad bits. The problem happened later when I was printing characters to the screen and reading back the memory, where I got thrown for a loop because of the Apple character set and how it repeats multiple times. There must be the quirk in the way AppleSoft Basic handles printing characters to screen, because originally I had it right where I thought that the @ symbol was actually hex 80. But when I was looking at a machine language monitor at the values that were actually in memory, when I printed an @ symbol from Basic, I actually was seeing C0 in memory and not the A0 that I thought it was going to be. Well, the problem is both of those characters, A0 and C0, render the screen exactly the same way. I think with the bad memory bits, the spaces were turning into the A0 @ symbol, but when I printed with Basic, I was getting C0. So that's where I was getting tricked, and I thought the space was turning into a C0 instead of the A0 it was actually turning into. Even though I got it right when I was doing my first calculations, the correct way to really validate that I was doing it correctly was to read the exact memory location which had a bad bit. Because remember, it was just a few of them on screen, and then I would have actually seen the value that it was turning into and not made an incorrect assumption about it turning into C0 instead of A0. Also, today I learned that you really cannot trust the built-in diagnostics, but I'm really not surprised. I have no idea what routines it's using for RAM checks, and clearly it's crap, because I think it said bit 6 was bad, and that chip is still in the board, and it's working without issue. Bits 1 and 5 were our problems, and the only thing I'm happy to report is, at least with my manual calculations, even though I had bit 6 as one of the bad bits, if I had changed all 3 RAM chips, that wouldn't have been a big deal. The computer would still work, obviously. If we had followed what the built-in diagnostic said and changed out just 6, or 5 and 6, and then 6, well, the machine still wouldn't have worked, because bit 1 was also bad. So if you have a IIc that has bad RAM, or another Apple II that has bad RAM, and you have an EEPROM programmer, I really do recommend try out the dead test ROM. As you saw, it did give us the correct information on which chips were bad, and that helped me fix the machine with the minimal amount of desoldering. Every time you take a chip off a board, you risk potentially damaging the board, so I really recommend just trying to do a minimal amount of desoldering if possible. And then, of course, for this machine, we also had bad speaker. That's kind of odd, but yep, that was bad. And then we had that bad hue control where that was out of adjustment, so the colors all look terrible. So just tweak that, and that looks a lot better now. So that's going to be it. I hope you enjoyed this repair video. If you did, thumbs up. I know this is all kind of run-of-the-mill stuff, and I kind of went on and on and on for quite a long time about how to figure out which chips are bad, but it's kind of what I do. I like to try to teach people how to be able to figure that out for yourselves using the tools you have available to you, which is your eyes and your senses and a machine language monitor, and then we resorted to the dead test just to see what it would do, and it actually corrected my mistakes with my little manual calculations. So anyways, if you liked it, thumbs up. If you didn't, you know what to do. Huge thanks to my supporters. Thank you very much, James, for giving me this machine and all the other machines. Thank you to all of my subscribers. Hit that subscribe if you haven't already. Makes a big difference. And I guess that's gonna be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.